Greetings and welcome to the pod. My name is Mark West, and do you think you can ocean swim on other planets? The answer is maybe, but not just yet.
You know, that's the joy of exploration, and you never know, in a few generations there may be people actually trying those extreme sports rather than just talking about it. If we ever do definitively show that Titan is sterile, say that there's no life there, then that would clearly open it up as an extreme sports destination in the science fiction future of affordable space travel.
That's forward looking. I hadn't thought of that.
Yeah.
I spoke with Associate Professor Jonty Horner, an astronomer and astrobiologist who works in the Computational Engineering and Science Research Centre at the University of Southern Queensland. We caught up for a chat at the Australian Space Research Conference. It's currently thought that there are oceans scattered throughout our solar system, although some better hidden than others, and that there are oceans throughout the universe. I started by asking Jonty about the long-held idea that Earth is the only place in the solar system with water and oceans.
Now, that's about as far from being true as it could possibly be. So water's one of the most common things in the universe, and it's one of those common misnomers that water's rare. Water is everywhere. Liquid water's the rare bit. So the comets that we see sleeting through the solar system all the time, that we see, you occasionally get a really bright one and it makes big news, like Comet McNaught a decade ago, that many of your listeners will have seen shining spectacular in the evening sky, was a dirty snowball. It was mainly water. And there's so much of that around. Water is very, very common. And the reason for that is hydrogen is the most common thing that there is. It's 75% of all atoms in the universe are hydrogen atoms. Oxygen is the third most common atom. And the thing that they form when you put them together is water. So water's everywhere. But to get liquid water requires the right range of temperature and pressure conditions. So it's kind of Goldilocks but turned up to 11. You need to be the right temperature but the right pressure, but, all these kind of things. And that's why liquid water was thought to probably not be that common. But as we're learning more about the universe, but particularly about the solar system, we're realising that liquid water and just liquid might not be as rare as we thought.
And that's fascinating. So the first time I heard about water, liquid water on another planet, it wasn't a planet, it was Europa, the moon of Jupiter. But now it's thought to be on a bunch of moons of Jupiter and Saturn.
And all over the place. So the current thinking is that Europa probably has significantly more liquid water on it than the whole of the Earth by a factor of 100 or 1,000. It's not even a small difference, which sounds really weird. Europa is about the size of the moon, so it's much smaller than the Earth. Its surface is this beautiful opalescent white ice sheet, and beneath that we think there's an ocean 100 kilometres deep that girds the entire satellite, which is a vast amount of liquid water there. At the bottom of that ocean, there are probably volcanoes, sub-ocean vents spewing material and energy into the ocean. So you've got the perfect mix. You've got liquid water, you've got nutrients, and you've got energy. And everywhere we find those things on Earth, we find life. So that obviously prompts a lot of science fiction, a lot of very excited and animated discussion about could there be life beyond the Earth? Could Europa be one of the best places to look? Of course, the problem there is to go look. We've got to get through 10 kilometres of ice sheet. So it's not an easy task. It's not an easy question to answer.
And that's the point. So even on Pluto, however many hundreds of thousands of kilometres away, there's thought to be liquid oceans as well.
Potentially. So these would be very deep buried oceans, which is kind of quirky. We're not talking here oceans on the surface beneath an atmosphere. We're talking about an ocean that is below and above rock or ice or whatever. So it's a liquid layer surrounded by solid on both sides. It's almost like having a sweet with a liquid interior.
Yeah.
Something like that. And that's very alien to our expectations. If you go down to the beach in Sydney, that's a very different experience to if you're in the ocean at Europa or the ocean at Pluto. But those oceans are still there. We're still getting more and more confident that a lot of objects in the solar system have these soft liquid centres.
And it's quite likely to be less than zero, is that right? It's going to be pretty salty.
It will be pretty salty, pretty cold, pretty slushy. But not necessarily everywhere. So if you've got volcanic activity at the bottom of Europa's ocean, the areas around the vents will be scalding hot, just the same as at the mid-Atlantic ridge on Earth. You're talking water that's superheated, that's above 100 degrees.
Right.
So you've got a full range of temperatures, pressures, and I'm not a biologist, I'm not a geologist, so my knowledge of what goes on around the black smokers and the white smokers is a bit hazy, but my very dubious recollection is that you get a temperature gradient. Obviously, you've got hot water, you've got cold water, and between them the temperature varies from one to the other. And you get different species that live at different temperatures, so you get a species gradient going away from it as well, where different types of life are adapted for the different conditions and lie at different distances from the smoker. And that's the kind of thing you could imagine elsewhere. No evidence that it actually is the case, but imagination often drives science and takes it to interesting places.
It's fascinating. And then there's not just water oceans, but I'm thinking Titan here, moon of Saturn, maybe hydrocarbon oceans.
Titan's interesting. So Titan's the only other place we know where there is liquid water. Well, not liquid water, sorry, where there is liquid on the surface of another object with an atmosphere above it. So liquid that is exposed to atmosphere. Rock underneath, atmosphere on top. Well, I say rock underneath. On Titan, the bulk of the rocks are water. The rocks that are harder than granite are water ice. The liquid is liquid methane and ethane. You get methane and ethane rain, you get clouds, you get weathering, you get stream beds. And all of this we know because we've sent our robot envoys out to Saturn. They've orbited around Saturn, we've dropped a spacecraft onto Titan, and we've got remarkable images and radar back. And if you turn off the fact that it's 100 and tiddly-pom degrees below freezing, if you turn off the fact it's smaller than the Earth, if you turn off the fact that Saturn looms large peeking through the clouds, you look at those photos and they're very reminiscent of what you see on Earth. You've got winding river valleys eroding their way through the bedrock. You've got lakes, you've got oceans. It looks very much like home, except for the fact that those oceans are not water, they're methane, they're ethane. Except for the fact that the raindrops would probably be more than an inch across and would float down slowly rather than hammering down hard because of the lower gravity. Yep. It's all very, very interesting, but Titan is also probably the only place we know of where there are multiple oceans in different locations. What I mean by that is that it's got a surface ocean, the methane and ethane, but again it probably has a soft centre. It's probably got a layer of liquid water buried deep beneath, maybe 100 kilometres, 200 kilometres down, just like Europa, just like Enceladus, just like potentially Pluto. The more we learn, the more we're realising that oceans are everywhere, even if they're buried deep and hard to find.
So that's the place to go swimming.
It is if you had sufficiently temperature-resistant scuba gear.
Yeah.
It would be interesting, actually. I don't, off the top of my head, know enough about the physics of buoyancy, mobility, and the drag you'd get in fluids other than water to know what swimming in the hydrocarbon oceans on Titan are like. I mean, it might be very glutinous, very gloopy, because it's very cold, but equally, that it's very cold for water, but it may not be very cold for methane and ethane, so the density might not be that high. You may not be buoyant. I don't know. Now, these are things that other people have probably answered, and I just don't have at my fingertips. But as soon as you take it from the science to the extreme sport angle, I guess, you bring in a whole new wealth of science that you need to answer, to study, to actually try and get a feel for what it would be like. So a lot of what you do when you're swimming, when you're scuba diving, is actually very, very scientifically driven. Yeah. The knowledge that we have that allows us to do this is based in the science that we study, and it exposes people to new questions. I think this is great because if you can find something that people love doing, something that inspires people, that can be a doorway through which they can actually see the beauty and the excitement of science that a lot of us as scientists take for granted. But a lot of school kids, for example, really struggle to get because it can be taught in quite a dry and unapproachable way. Yeah. But if you can hook it into something that people are passionate about, then they can see the benefits and the merits. And we all know what it's like when you get excited about something, you'll follow it through to its conclusion and learn a lot on the way.
Yeah, that's interesting. I mean, oil floats on water, but that happens at 20 degrees here.
Yeah.
So who knows?
Exactly.
Minus 100,
all
200.
So hard to imagine, so different
to
what we have here. But that's the joy of exploration, and you never know. In a few generations, there may be people actually trying those extreme sports rather than just talking about it. If we ever do definitively show that Titan is sterile, say that there's no life there, then that would clearly open it up as an extreme sports destination in the science fiction future of affordable space travel.
That's forward-looking. I hadn't thought of that.
Yeah.
Well, speaking of space travel, then we've talked about our solar system, but what about outside our solar system? What about exoplanets? Have we found water, oceans anywhere else?
We've not definitively found oceans. We have found water. The challenge here is, of course, that exoplanets are so far away they're very hard to learn about. We've found over the last 20 years more than 3,500 planets around other stars. When I grew up, when I was a teenager, I lived in a world where we didn't know if the solar system was unique. We didn't know of any planets beyond the solar system. And there is now not a teenager on the planet who grew up in that world. The first planets around other stars were found 20 odd years ago now, which is breathtaking. The problem is, they're so far away we don't image them. We don't gain clarity on what their surfaces look like, things like that, very readily. 99.9% of all the planets we've found indirectly. We've seen a star doing something unexpected, or we've inferred that there's a planet there with it. And we can then learn more about the planet. We've got a very small handful, about 10, where we've actually imaged them directly and we've seen a single point of light moving around a star. And they're our best images of planets around other stars, a point of light. Now, that's a bit more pessimistic sounding than the actual reality, which is that once we know a planet's there, we can learn more about it. So people have begun to learn about the atmospheres of some of the biggest, most massive planets. So these are planets much more like Jupiter than like the Earth. And you can do that by taking account of chance alignments. If you have a planet that passes between us and its star, we get a transit, and that's how many planets have been found. It blocks out part of the stars, like the star gets a little bit dimmer, then a little bit brighter again. A logical follow-through on that, though, is that if you've got a star passing between us, a planet passing between us and a star, then the light from the star, a tiny fraction of it will pass through the planet's atmosphere, and that will imprint the signature on the light of what the composition of the atmosphere is. And that's a very tiny signal, very hard to detect, but people have done it. And there's a growing list of elements and of compounds that have been detected in the atmospheres of these behemoth giant worlds, and water is among them. And that, again, shouldn't be a surprise. Water is everywhere. The trick is finding, from the point of view of life and from the point of view of extreme space tourism, travelling decades or thousands of years to get to a destination is a long holiday and it's hard to get the leave for it. But finding destinations for that is a little bit beyond us at the minute. We're not at the point yet where we can get that degree of characterisation. It's coming. With TESS, which is NASA's next great mission, the Transiting Exoplanet Survey Satellite, we'll start to find planets down to the size of the Earth and smaller around some of the brightest stars in the sky and some of the nearest stars that we have. And that'll give us a really good hint as to how common are planets like the Earth and planets like Venus. And that's a first step along the road to actually finding somewhere that is truly Earth 2.0, where you could go surfing, where you could go scuba diving, and probably try and avoid getting devoured by the local predators that will be totally different to anything we've got here.
I've heard the opinion that it's perhaps decades, but so not too far that we'll be actually able to look at exoplanets, maybe not through a telescope from Earth, but from the sky, and actually image whatever continents and oceans that are there.
There are missions proposed for that, and it's incredibly challenging to do, but if you look at the spiel for some of the space telescopes that are proposed and are competing for funding to launch in the 2030s, that's the kind of work they're proposing. There was a lot of discussion a few years ago about the Terrestrial Planet Finder, which was a proposed mission. And one of the things they were spruiking was that they'd have the resolution to start getting multi-pixel images of Earth-like planets. Now that's, I think, a bit of a stretch, but it's doable. The problem is that these things are so far away, they're very small on the sky. And so to resolve them, you either need a single telescope that's incredibly wide, or you need to develop a technique like interferometry, where you can use telescopes that are very widely separated to simulate a much, much bigger mirror. And that's going to be the trick that's needed there. Now, interferometry, we've got grips on. When you're talking about radio waves, radio interferometry is now kind of passé, very long baseline interferometry. It's one of the many things that the square kilometre arrays are going to be doing in Western Australia. Is a really big deal. But that's where you've got very long wavelength radiation. So you don't need to be as precise in where you put things. The shorter the wavelength, the more accurately you've got to be able to position things to do this. And light has wavelengths measured in a few hundred nanometers. That's a few hundred times 10 to the minus 9 meters. Many times smaller than the size of a human hair. The radio waves you're using have wavelengths measured in meters. So we've got to get a factor of 1 billion times better to do the same tricks with visible light as we do in the radio. And we're getting there, but that's a big technological challenge. And the beauty of this, going outside of just looking for planets like Earth and trying to image them, is that the technologies we develop to do that, then trickle down into every other part of life. So there's a real benefit to the listener who's not really actually that interested. It's a planet so far away, why should I care about these developments? Shouldn't we spend the money elsewhere?
Yeah.
Well, this will birth new technologies. It will help medical imaging. It will lead to all of these developments that would not happen otherwise. And that, in all honesty, is why NASA is funded so highly. The US government is not particularly interested in astronomy. Yes, it's nice to get kids into STEM, but what it's really interested in is pushing the boundaries of technology back. And space exploration and space telescopes are an incredible way of driving new technologies that then become hugely profitable and hugely beneficial in other areas.
Yeah, for all the talk of various markets and whatever, if you trace back so many technologies, it comes out of publicly funded science.
It does, and then somebody patents it and makes a lot of money out of it.
Yeah, that's right.
You know, I believe the Australian government has a huge earner in the form of Wi-Fi. Wi-Fi was born of black hole research.
Right.
The protocols that we now use to post derogatory comments on the internet about how CSIRO are not pulling their weight are all done using technology that CSIRO developed,
Yep.
which I think is one of the vaguely entertaining ironies.
Yep.
You know, that people use a technology that was developed by someone else to criticise the person who developed it without realising what they're doing, you know.
There's a great joke about climate deniers waking up and using CSIRO technology to connect their phone and checking the Bureau of Meteorology app. You know, all this stuff developed by Australians. And then, yeah.
Absolutely.
It gives me, there's some things, so some of the technology sounds, far-fetched and a long way away, but I think of particle accelerators and, CERN and places like this where the mirrors are, engineered to the half a width of an atom and things like this, so it's not...
It's astonishing what we can do, and it's not that far-fetched. As you say, a really good example is mobile phone technology. I remember as an undergraduate in 97, 98 having my first mobile phone, and it was a Nokia brick. It weighed about the same as most computers do these days. And a few years later, the first phones came along with kind of vaguely pretty screens, and then phones got smaller and smaller and smaller until people realised they could watch videos on them, and then they got bigger and bigger and bigger again. And now I have a phone in my pocket that is more powerful by far than the first computer I owned 20-odd years ago,
I think
30 years ago.
Yeah, their orders of magnitude more powerful than what we sent Apollo to the moon with, right?
Yeah, I had a calculator watch as a nerdy teenager that was more powerful than the entire infrastructure they used to put man on the moon.
That's amazing, isn't it?
And that was in the 90s.
Yeah.
Technology advances at a breathtaking rate, and a lot of it is driven by the blue sky science in ways we can't predict, and it isn't a predictable thing. You can't say if we invest in this particular science project in 10 years' time we'll have hover cars. It doesn't work that way. You don't know what the outcomes are going to be, but they're going to be there, and smart governments invest.
Yep.
And my understanding is actually that that's how the US finally broke the back of the Great Recession, was that a forward-thinking president decided to invest a lot in science and set up publicly funded colleges and research institutes, put a lot of money in, and the economy boomed.
So what's the next, well, what are the missions that are coming up that are going to go and swim in these oceans we talked about?
That's a little bit far away. So the cycle on which missions happen is quite lengthy. Good example is that in 2007, I went to a workshop in Paris talking about a potential mission to Jupiter to orbit and visit its icy moons. That mission is still being developed and hasn't even been accepted yet 10 years on, and wouldn't fly until the mid-2030s. So the cycle is such that PhD students working on a mission now will be the chief scientists by the time it happens. It's breathtaking long timescales, and that means that a lot of these missions are put together and run on timescales that aren't just 1 or 2 political cycles, but are closer to 10 political cycles. And that's why they can be a little bit funding sensitive, with the back and forth that goes on. These are prepared on timescales longer than the average boom-bust of the global economy. It's kind of breathtaking. So it's very easy to talk about the missions that will launch in the next few years, and the further in the future you go, the more you're bound by speculation. But we've got incredible exploration going on at the minute. There are 2 missions currently in space on their way to touch down on asteroids and bring samples back. And that's Hayabusa 2, a Japanese mission going to the asteroid Ryugu, and OSIRIS-REx, which is a mission going to the asteroid Bennu. And they're going to touch down on asteroids and bring samples back for people to use in the lab, which means we're at the frontier of being able to go to asteroids, bring things back from them. Hence, we're going to see the dawn of commercial asteroid mining.
Yep.
Within the next 10 years, we're going to see companies putting spacecraft onto asteroids to mine the rare earth metals or to mine the water within them. Believe it or not, water is actually one of the most valuable commodities because you can break it down into hydrogen and oxygen and use it as fuel.
Right.
So if you can send water back to your satellites in orbit around Earth, you can refuel them, extend their lifetime to save a huge amount of money.
Yep.
And that's just one of the many frontiers we've got coming on. We've got the incredible Juno mission orbiting Jupiter at the minute. And that has a camera tacked on, not quite as an afterthought, but certainly as a non-scientific component to the mission, called JunoCam, which is designed for outreach and engagement to excite people. And it's sending back the most breathtaking, spectacular images that are made freely available immediately for people to process. And the global enthusiast community has been making hay with them and making the most stunning visualizations as a piggyback on the science. There's great science going on as well, but what's capturing imagination are these incredible images.
Yeah.
Going further forward, we've got TESS launching next year, which is a transiting exoplanet survey satellite that will find myriad worlds around distant stars. The James Webb Space Telescope will launch at some point in the indeterminate future. The reason I say that is that I think it was originally scheduled to launch in 2011, 2012, and has receded in time by 1 year per year.
Right.
Almost, as technology challenges came up, as financial challenges came up. I think it's currently scheduled to launch next year or the year after, but I'm more confident that TESS will launch on time than I am that JWST will launch this decade. Further forward, it gets more woolly. There has been a proposed Europa lander that has been heavily discussed in the US, and there have been a lot of studies done, but the future of that and the funding for that looks very uncertain at the minute as a result of last year's election. That's one of the things that was an easy cut, so it may not happen. The Europeans are looking at the JUICE mission, which is going to be, it's probably been renamed again. This is the one I went to the meeting about back in, actually I think it was 2005, not 2007, all that time ago. And that's looking at having a spacecraft that goes to Jupiter and orbits the icy moons to learn more about the oceans inside them, and to map them in exquisite detail so that the next generation of missions afterwards can identify potential landing sites.
Yep.
So if we're looking at landing on those moons, we're probably talking in the 2030s at the earliest, probably the 2040s, by which point I'll be getting to retirement age. And I was at that meeting whilst I was on my first postdoc.
Right.
It's the timescales people work on and the coordination, collaboration involved is mind-blowing. And the results are breathtaking.
It's interesting. I wonder, do you think that cycle will speed up or slow down? Because technology is arguably, depends on your scale, is speeding up, but then there seem to be more political challenges these days.
I would find it hard-pressed. I think things take longer now than they used to some degree. If nothing else, we went from the announcement of the attempt to put a man on the moon to having a man there in 6 years. Yep. Whereas the Jupiter orbiter missions, we're talking 20 or 30 years. You also have a fundamental wall, which is the time it takes you to cross the depth of space to get to your destination.
Yeah, there's some limits here, aren't there?
There are.
Even if we cut that down by half, it's still
a long time. Now, there are technologies that are shortening that time. So the New Horizons mission that flew past Pluto was enabled by newer technologies that wouldn't have been possible 10 years earlier. And it got to Pluto within a decade, which is just remarkable. That's the fastest we've ever launched something from Earth. It's not the fastest travelling thing we've ever produced because we've got other objects that have been slingshot by the giant planets. But in terms of travelling under its own impetus, it's the fastest thing we've ever built, which meant it got to Pluto in only 10 years.
It's going to catch Voyager 1 and 2 pretty soon, isn't it?
It'd be a while yet. I think Voyager 1 and 2 are probably actually travelling a bit quicker than New Horizons because they got the benefits of multiple slingshots past the giant planets.
Okay.
But the difference is they've been helped.
Yeah.
New Horizons wasn't. And as this technology comes on board, we've got incredible missions like the Dawn mission, which is flying around in the asteroid belt, where we've now got the level of technological sophistication to send a spacecraft to an asteroid, move into orbit around the asteroid and image it for a year, then pack up your bags and go to another one and move into orbit about that and image it. That's
amazing.
Incredible. It's beyond what I could have imagined as a teenager growing up really excited and enthused about astronomy.
Any of those asteroids big enough to hold underwater oceans?
It's funny you mentioned that. Ceres, which is where Dawn is at the moment, is the biggest object in the asteroid belt by far, and we think it's wet. And there are indications that whether it has a subsurface ocean now, it may well have done in the past, because all these things are limited in time. In the case of Europa, and in the case of Enceladus, they're kept warm inside potentially at least, in the case of Europa, by tidal energy. Jupiter's this huge planet nearby pulling and torquing Europa, dumping huge amounts of energy into it, which keeps it warm, keeps it wet on the interior. But for Ceres, the only thing keeping it warm is the radioactive decay of the elements that were incorporated into it when it formed and the residual energy from all the collisions that formed it. And that's time limited, it's cooling from the outside in. So it would once have been warmer than it is now, and any ocean would freeze. The same's true of plate tectonics on the Earth and Mars. Eventually, the interiors will cool to the point where they lock up.
Yep.
And so the planets freeze out from the inside out. Everything is fixed in time, is limited in time. I mean, even the Earth, the oceans will not be here forever. In a little while, the sun is growing more luminous as time goes on, the Earth will become too warm to support the oceans and they'll boil. That's about 500 million years away, so we don't have to worry about it too much
So
yet.
the Earth will boil before it freezes?
Yes, absolutely. The Earth's oceans will boil 500 million years to a billion years in the future, and then it will become a hot house, hellish world like Venus. Then, much further down the line, the sun will turn into a red giant and may devour the Earth.
Yep.
If the Earth survives, then when the sun comes to the end of its life and blows off its outer layers, leaving a tiny white dwarf as a remnant, the Earth will then freeze.
Yep.
And will become a tiny desolate speck freezing in a dark and miserable cosmos. What a cheerful concept, right? But fortunately, it's a long time in the future, and if we're still around, we'll have gone far beyond the Earth by then.
We'll figure that out by then.
Yeah.
It's actually, as you were saying that, it was just sort of occurring to me that oceans shouldn't be that unexpected, right? If water is everywhere and all planets and moons start off hot, it's going to go through a stage and cool down, and it might be mushy or something, but you're going to have liquid until it cools down, I guess.
If you get lucky, I mean, you even have the concept of the interiors of giant planets
Yep.
have large amounts of water in them. Uranus and Neptune have interiors that are probably actually incredibly hot water ice.
Yep.
Whether there's an ocean or a slushy component to that is beyond my knowledge. You need to talk to someone like Helen Maynard-Casely, who's an expert in that kind of thing, to really get to grips with what conditions are like in the interiors of those planets. But there's a possibility at very high pressure of lots of different gases being liquid, because it's just one of the phases of matter.
Yeah.
So if you take things far enough, you can have the concept of seas of pretty much everything. Liquid metallic hydrogen in the middle of Jupiter. It's not necessarily somewhere you'd consider being particularly promising for life. You know, it's millions of atmospheric pressures and all the rest of it.
Yeah.
But liquids are not going to be uncommon in the universe. Liquid water is probably going to be fairly common. It's just a journey of discovery, it's a journey of exploration, and we're just stepping out on it as we speak, basically.
It's probably a stretch to call Venus's lava flows oceans, I guess, but there's melted metallic.
The interior of Venus is slushy liquid like the Earth. It's a magma ocean buried beneath the crust, and there is a certain body of evidence, so I don't think it's universally accepted, that Venus resurfaced about 500 million years ago, and the entire surface would have been molten for a time, or it may have done it episodically in parts.
Right.
But go back in time, and you get to a time when the solar system was much wetter than it is now in terms of liquid water. We think 4 billion years ago, just after the planets formed, Venus, Earth and Mars would probably all have had oceans, and would have all looked very, very similar. And what they are now is a product of 4 billion years of evolution.
Yep.
Under different conditions, Venus being closer to the Sun, Mars being further away, the planets being different masses, have a different history. And it's like, I guess, having a set of triplets who are essentially the same when they're born, but by the time they're 30, they're living very different lives, having had very different experiences. Yeah. And those planets have evolved down different paths because of the environment they're in. And we're just lucky that the one we're on is still capable of supporting us, at least for the time being.
At least for a bit. Yeah.
Yep.
Until we ruin our oceans. What's next for your research? What are you working on?
We've got a fair few interesting things going on at USQ, but I think the highlight for the next year or two is a project we're setting up called Minerva Australis. And this is tying into NASA's test mission. It's basically USQ getting involved, working with NASA hand in glove. The test mission is going to find thousands, tens of thousands of planets, but all it really tells you is that there is a planet there. To learn anything more about it, and even to confirm that the planet is really what we think it is, you need to do follow-up observations from the ground, and that's very challenging, very time-consuming. And in all honesty, there just aren't enough telescopes worldwide to do it. It's very hard to get time on the world's biggest telescopes. And to do this kind of work, you really need dedicated instruments that can look every night of the year that it's clear. Yeah. So that's what we're building at USQ. We've got a new multi-million-dollar facility that they're literally working on while we talk. They've poured the concrete, they've put the building up. We're now getting ready for the telescopes being delivered and all the rest of it. That should be on Sky about the same time that TESS launches. We'll have 6 telescopes feeding light into a spectrograph. Basically, that's our big ticket science instrument. We'll also have cameras on them so we can do what we call photometry. We can measure the brightness of stars, or we can measure their light broken down into its various colours to look at the spectral lines, see how they move. What that will give us the ability to do is to follow up on the TESS observations. The minute they say, we think we found a planet, we can jump into action and confirm it for them. We can then learn more about it. We can figure out its mass. From knowing its mass and its size, we can get a feel for its composition. We can get a feel for what kind of planet it is. So it's going to be a really exciting opportunity for us, if nothing else. I mean, how cool is it that a small university in the middle of the Darling Downs in southeast Queensland is working with NASA to find planets around other stars? Yep. I think that's just brilliant. And that's going to be fabulous for the community around Toowoomba as well. It really puts Toowoomba on the map. It's going to be a global exposure for a beautiful area. Yep. We're involved with a few other things. My boss, Brad Carter, and his team look at space weather, but they're not looking in our solar system at what's happening here. They're looking at space weather around other stars, which again is a really cool and interesting topic and plays into the astrobiology side of things again, in terms of, is the sun typical? Is the sun unusually active, unusually quiescent? What implications does that have for life? They're taking it one step further. You can almost imagine the work that they're doing leading us to being able to work out which of the planets we find get aurora like the Earth from their results. We can tie that together. Another project we're working with, which has been run out of Curtin University, is the Australian Desert Fireball Network, where we're putting cameras about the size of a lunchbox out on the roofs of buildings through rural Queensland, through rural Australia in the case of the rest of the network, to scour the sky all night, every night, looking for bits of space junk hitting the Earth's atmosphere and falling to Earth, remnants from the formation of the planets 4.5 billion years ago. And when we get those meteorites in our hands, we can do a lot of science with them that can help answer questions like, where did the Earth's water come from? Where did the Earth get the water that we take such pleasure in using? Where did that come from? How did the planets form? And that's going to be essentially using Australia as a giant fishing net to catch rocks from space, bring them into the lab and do science with them. So I'm really lucky. I get to do my hobby as a job, which is an incredible privilege, but we're really lucky to be able to be involved in so many really cool and really exciting projects all at the same time.
Are you involved, or do you get anything out of the new Australian Space Agency, or whatever its official name is?
We may do. We know very little about what that's going to be. So all that is known about the Space Agency, as far as I can tell at the minute, is that it's going to be a thing, and we'll find out more next year. Right. There are going to be quite a lot of discussions at the conference I'm at this week, the Australian Space Research Conference, about what this might mean, what we should expect to look forward to, what information we can feed back into the process. There's a whole review undergoing and everything else. But at the minute, that's very much a holding pattern, wait and see. It's a great step forward that this is finally happening, but we need to know more details before we know whether it's going to have an impact on blue skies science, or whether it's purely going to be the domain of defence, Earth observation, Bureau of Meteorology, things like that. It's all up in the air at the minute.
That was Associate Professor Jonty Horner. If you'd like any more information on this episode, or on the podcast in general, get over to the website at www.thepodpodcast.net. That's thepodpodcast.net. And I'd really love to hear your feedback on the show, both this episode and what sort of topics you'd like us to cover on the pod. My name's Mark West. Thanks very much for having me. I'll catch you next time on the pod.